Hello everyone and welcome to this video. So we are again doing kinetic model of matter KMM questions. In the last video we did MCQs and now we're looking at structured questions. To speed up the working of this, I've already done the questions and we are doing the more difficult ones because the easier ones we've already done in class. For example, this one. So figure 1.1 shows a toy water rocket. The rocket is half filled with water and connected by rubber tubing to a pump. Air is then pumped into the rocket so that the pressure of the air inside the rocket increases. Explain in terms of particles why the air in the rocket exerts a pressure on the walls of the rocket. So this is a pretty easy question. We know how to tackle this. Why does pressure exist in terms of particles or in terms of molecules? This is basically the question that the examiner asks time and again. And the idea is this, that you basically just say the same three things all the time to get those 3 marks. Only in the case where the examiner says something like use ideas about momentum, then you would talk about momentum, and in that case this would be a 4-mark answer. Otherwise it's the same thing. So you start with this, that particles are in constant random motion. They collide against the walls of the container. This causes a force which produces the pressure. So 1st mark, 2nd mark, 3rd mark. Let's go on. Temperature of the air in the rocket remains constant as air is pumped into the rocket. So temperature is the same. Explain why increasing the number of air particles in the rocket increases the pressure of air in the rocket. So remember that pressure, according to your response, it's just directly linked to collisions. So if you have a greater number of air particles, there would be more frequent collisions. That leads to a higher air pressure. With collisions, remember that you clarify that these are not collisions with other particles. Rather, these are collisions with the walls of the container. We'll be skipping these 2 parts because this is linked to forces and momentum. And we're going on to another question. Let's talk about this one. So density of water in a lake is given like this. At a depth of 25 meters beneath the surface of the lake, the total pressure is given as this. So see that this is the total pressure. And why does it say the total pressure? Because at any point inside the liquid, you'll obviously have the liquid pressure, but the total pressure means that we also have added to this the atmospheric pressure. Anyway, part A says state what is meant by pressure. Very easy definition, which is just the formula but in words: force per unit area. Gravitational field strength in this question was 10, but when you'll be appearing for your exams, this would be 9.8, so we'll use that just to get the hang of this. Find the pressure due to 25 meters of water. So this is pressure due to the liquid, which means I just need to use that rho GH formula. So liquid pressure is rho GH, rho is density, G is gravitational field strength or acceleration due to gravity, which is 9.8, and H is the depth, which is 25. So this turns out to be 245,000 pascals. If you want, you can also write this in standard form, but it's not really required. Next, the atmospheric pressure, and for this we'll be using this phrase which was given here, which is the total pressure. So if this is the total pressure, that means it's the liquid pressure plus the atmospheric pressure, and I can use that to actually find the atmospheric pressure. So I just go ahead and say that the total pressure is the sum of liquid and atmospheric pressures. So rearranging this equation, the atmospheric pressure is the total pressure minus the liquid pressure. So 3.5 into 10 to the 5 minus 245,000. When you do this in your calculator, the answer would be 105,000 pascals, like this. An underwater depth gauge contains a small cylinder as shown in 8.1. Gas is trapped inside the cylinder by a piston. The piston is free to move, right? So this is basically used for measuring depth. So the next parts of the question, they say that the outer face of the piston is in contact with the water. As the depth gauge is lowered into the water, the piston moves into the cylinder. This moves a needle on a dial to indicate the depth of the gauge in the water, right? So that is not really drawn here, but this is told to us. And it says explain why the piston moves into the cylinder. So we know that as this moves into the liquid, into the water, so the outward pressure would increase because of that formula that we just saw, which is pressure equals rho GH. So as depth increases, the external pressure would also increase, right? Which we know is the sum of the liquid pressure and the atmospheric pressure. So when the outward pressure that's applying like this to the left is greater than the inward pressure which is being applied to the right, so there would be a resultant force inwards, and that would cause a resultant force on the piston to move into the syringe, right, into the cylinder. So that's the idea that I also write in this response here. First step, saying that the liquid pressure would increase with depth. Next, saying that the pressure outside would be greater than the pressure inside, and that causes a resultant force on the piston, causing it to move inwards. Next, the temperature of the gas does not change as the piston moves into the cylinder. Explain in terms of molecules what happens to the pressure of the trapped gas as the piston moves into the cylinder. So temperature does not change. This means that the examiner is about to ask us for the relationship between pressure and volume. So we know that as the piston moves inwards, the volume decreases. And now I need to talk about what would happen to the pressure. So because the volume decreases, the same number of particles are now trapped in a smaller space. I can say that there are more number of molecules per unit volume, right? So because of that, there would be more frequent collisions with the walls of the container. That would cause the pressure to increase, right? That's exactly what's written here. I've taken a slightly different angle here. So I've said that particles get closer together and they travel less distance, and that leads to more collisions, right? Because they're trapped in a smaller space. But you could also just say that the same number of particles or the same number of molecules are now in a smaller volume, right? So more number of particles per unit volume. So more frequent collisions, because in any reasoning regarding pressure, you will have to talk about collisions. So more frequent, that causes a greater force, leads to a higher pressure. At the surface of the water, the volume of the trapped gas in the depth gauge is V0. On 8.2, sketch a graph to show how the volume of the trapped gas decreases as the gauge is lowered into the water. So I know that as depth increases, the pressure would also increase, right? So I already know that at depth 0, which means it's right at the surface, the volume is V0. So this is the starting point of my graph. And I know that as pressure increases, the volume would decrease. But would the volume ever actually become 0? The answer is no, because of this inverse relationship, right? So in inverse proportion, neither quantity can become 0. It's only talked about theoretically, because for one thing to become 0, the other thing would become infinite. So then it would be a graph for inverse proportion. And what's different here is only that it would not start, it would not be, it would actually touch or cut this axis at this value, but it's not going to cut this axis, right? Now, usually the pressure volume graphs that we've seen, they look like this, but this one is obviously different, right? Because it's not exactly pressure volume, it's the volume of the trapped gas versus here this is the pressure due to the gas, and here it's the depth. So the only thing that changes is that there is a y-intercept here, otherwise the shape is the same, right? So this was a slightly tricky part. The instructions for the depth gauge state that each time it is used, the needle of the dial must be reset to 0 at the surface of the water. So just one reason for this. So when we're talking about the pressure volume relationship, remember that it assumes that the mass is constant and the temperature is constant. Now because nothing is leaking into or out of the cylinder, so the mass is constant, I can say that maybe the temperature varies. This is the suggest part. These are the most difficult parts of your P2 papers, and this is something that you have to think about. Density of the air trapped in the depth gauge increases, however, the density of the water remains constant. Explain in terms of the molecules of water why the density of the water remains constant. So if density remains constant in terms of the molecules, that's probably because the molecules cannot come any more closer together, and that's because of the repulsive forces between molecules. Now, how do I know they are repulsive forces? Is basically if I think about a molecule and another one, both of these would have a nuclei at the center, right? They have a nucleus at the center, so these would repel at very short distances. and they cannot come any closer together, right? So that's what you had to say here. Let's look at this question. A student uses a pump to inflate a bicycle tire. 2.1 shows the pump and the tire. Pressure of the trapped air in the pump is given as this. Cross-sectional area of the piston is given as this. Calculate the force exerted on the piston by the trapped air in the pump. So pressure is force over area. I can just reorganize that formula and make F the subject. So F equals pressure times area, which turns out to be this value, to 2SF. I can say that's 230 newtons. The student pushes the handle to the right and the piston forces the trapped air into the tire, right? So the trapped air then goes into the tire. The force exerted by the student is less than the value in A1. So this means that the inside force was 230 like this, right? This is what the trapped air applies on the pump. But when the student has to push this, he actually applies a lesser force than this, and you have to suggest reasons for this. So we know that the resultant must be inwards for this to be going in. So I can say that one possible reason could be atmospheric pressure, which also adds on to the resultant, and that basically causes the piston to move in. Next, temperature of the air in the pump remains constant as the handle moves to the right. Explain in terms of its molecules why the pressure of a gas increases when its volume is decreased at constant temperature, right? So why does pressure increase when volume is decreased at constant temperature? So again, we've talked about this. So when volume is decreased, so you know that the number of molecules increase per unit volume as molecules get closer. Molecules collide more frequently with the walls is something I should have said here. Let me in fact write this: with walls of the container, applying a greater force. Let's go on to the next question. This is something we are interested in. A fixed mass of gas in a glass tube is trapped by a seal at one end of the tube and by a column of mercury. The mercury is free to move within the tube. The tube is rotated slowly from the vertical as shown in 3.1 to the horizontal as shown in 3.2. Volume of the gas increases and the temperature remains constant. Describe why rotating the tube changes the pressure of the gas at the seal end. So here you can see that this gas has expanded slightly, while here it has a slightly lesser volume. And the reason is this, that when it's in this vertical orientation, the mercury is on top of it, so it applies a pressure. That pressure is obviously not present when the tube is horizontal. Explain using ideas about particles why pressure of the gas decreases when its volume increases. We just talked about this, so I won't be wasting time with this here. So in 3.1, the length of the mercury shown is 0.3 meters. Density of mercury is given, atmospheric pressure is given. Calculate the pressure of the gas in the tube. So if you look at this diagram, it's talking about 3.1. So there is the atmospheric pressure which is also acting, but there's also the liquid pressure acting. If the gas is not being forced or if it's not being compressed further, this means that this inward pressure equals this total outward pressure, which is the sum of both of these. So in a way, it becomes really similar to those total pressure questions. So you find the liquid pressure using rho GH, values are given, rho G in our syllabus. So this is like a very recent syllabus paper, 2023. So small g is not going to be given. It's just given once at the start of the paper. So you need to know that. The length 0.30, you just work this out. This turns out to be 41,000. Atmospheric pressure is given 1.0 into 10 to the 5. You add both of these, so that turns out to be 141,000 pascals. Part C. The pressure of a different sample of gas changes at constant temperature. 3.3 shows 1 point marked X on a graph of pressure against volume for the gas sample. At X, the pressure of the gas is P0, volume is V0. On 3.3 sketch the graph as the pressure of the gas decreases from 2 P0 to half P0. So 2 P0 to half P0, these are some important intercepts. And how have I plotted these points? That's basically because of this inverse proportion. If this is my first point, so I know that, for example, when volume doubles, pressure would half. So if this became times 2, this would become times half, and this is that intercept. Similarly, in going from here to here, the volume halves, so the pressure must double and become 2p naught, which is this intercept. And as we just saw, now the graph is going to be a smooth curve, not a line that joins all of these. So something like this is what we are going for. Let's move on. We did this one in class. This one is something we want to do. Use the relationship between pressure, force and area to explain why it is harder to cut something with a blunt knife rather than with a sharp knife. So with a sharp knife, the area reduces and the same force which would be applied now causes a greater pressure. The same force is applied. I've confused this with another question, so I've written to the entire knife, but you would say to both knives, area is lesser for the sharper knife. That gives rise to higher pressure. Experimental procedures, experimental measurements on gas pressures were made by Robert Boyle. He showed that this is P1V1 equals to P2V2. State two quantities that must remain constant when this equation is used. So the two assumptions are that the third quantity, which is temperature, must remain constant, and the mass of the gas must also be constant. 5.1 shows the molecules of gas as the volume of the gas is halved. The equation suggests that when the volume of a gas halves, the pressure doubles. Using ideas about molecules, explain why this happens. So pressure doubling means that the molecules now collide more frequently, but exactly how much more frequently? Twice as more frequently, and that creates double the pressure. So you need to be clear with your wordings here. Last question. 4.1 shows a cylinder with a piston that contains a gas. A liquid occupies a much smaller volume than a gas which has the same number of molecules. Explain why there is this difference. So for a gas, you have negligible or zero intermolecular forces. So in that case, the particles can spread out much more and occupy a greater space. So there's a lot of distance between the molecules. Or you can take the reverse reasoning, and you can say that because of the stronger intermolecular forces in liquids, there is much less distance between molecules for liquids as compared to gases. Volume of the gas changes from V1 to V2 as the piston moves into the cylinder. This increases the pressure from P1 to P2. Temperature remains the same. State the formula that is used. So we know the equation, P1V1 equals P2V2. Initial pressure of the gas in the cylinder is this much. Initial volume is this much. Cross-sectional area of the piston is 5. The piston is moved in a distance of 8. Calculate the final pressure of the gas in the cylinder. So I have P1, I have V1. I can work out V2 and then find P2. So this is the initial volume, which is 100. Then it says that the piston moves in through a distance of 8 centimeters, right? So that means that if this is 8 cm and if this area is 5, so basically it moved in through 40. And now with the piston here, what would be the new pressure? What would be the new volume? That would be 100 minus 40, which is 60, right? And that is what we would use because that's our V2. That's exactly what I've done here. So 100 minus 5 times 8, which is 100 minus 40, which is 60. And then you cross multiply. This is the pressure value that you get. Last part, explain using ideas about molecules why the pressure changes. This is obvious. Pressure is obviously increasing, so there must be more frequent collisions with the walls of the container. So these were some of the questions. They had some pressure parts as well, which you should not be worried about if you are just right now preparing for the kinetic model of matter. But it is closely linked, so some ideas will be common. So anyway, that was this video. Like this video, comment if you have some confusions or questions still, and subscribe to the channel for more content like this. And I'll see you in the next one.